Welcome Math 107 students to the demo for lesson number 1. These are some selected problems from your prerequisites chapter, which is chapter P of your textbook. So let's get started by taking a look at the first problem. There's a couple of things going on in this problem. One is you see exponents like 300 and 600, but you also see the fractional exponent 1/3, and this often causes students some problems in terms of remembering what does raising something to the 1/3 power mean. Well, let's start with a little simpler problem over here to the right. 8 to the 1/3 asks us to find the cubed root of 8. This is the same as the cubed root of 8. The number in the denominator of your fractional exponent always tells you what root to take. So this is the root. The numerator does what it always does. It tells you to apply that exponent. And in this case, since the numerator is 1, there's nothing to do here except to take the cubed root of 8. Now remember, with odd roots, you can take the odd root of both positive and negative numbers. In this case, the cubed root of 8 would be 2. The answer would be 2. Okay, so that's just a quick review of fractional exponents. So what's going on here is we have to apply an exponent property, several exponent properties to this problem in order to solve it. So there's two basic exponent properties we're going to use here. The first one is a product. Product meaning you have a bunch of factors inside your parentheses, which means everything is being multiplied, and your product is being raised to a power. That's what we call this property, a product to a power. And in this case, the power attaches itself to each factor, and you're done. Okay? The second property we're looking at here is called a power. Since b to the m is a power, and that power is being raised to another power. In that situation, you simply multiply your two powers. So let's take a look at this problem A. The first thing I see is that I have 3 factors: factor number 1, factor number 2, and factor number 3. So each of these factors under the product rule have to be attached and somehow to that power 1/3. So we're going to just raise each one of these to the 1/3 power. Okay, so that's my first step. Now to simplify this, now that I've reviewed what this power of 1/3 means, it says find the cubed root of 64. So you're looking for a number that you multiply 3 times. 4 times 4 times 4 in this case will give you 64. So this simplifies to the number 4. Okay. The next situation is going to use this property right here, a power raised to a power. So you simply multiply these two powers here. So 300 times 1/3, and then y to the 600 times 1/3. And now you simplify those. Well, multiplying by 1/3 is exactly the same as dividing by 3. So that's 300 divided by 3, so that's x to the 100. And 600 times 1/3 is the same as 600 divided by 3, which is y to the 200. And you're all done. Okay. So you've used 2 properties of exponents, and then you simplified the constant raised to the 1/3 power by understanding what it means to raise something to the 1/3 power. Okay. So B is just a little bit more complicated than the problem I started off with. Remember, I started off with 8 to the 1/3 power, and we said that that was the same thing as the cubed root of 8, and our answer was 2. So now what does this say? This says, number 1, take the cubed root of 8. Number 2, square it. And number 3, apply what it means to be a negative exponent. When you have a negative exponent, you take your base, whatever your base happens to be. Remember, 8 here is our base. And you invert it. So you invert, or some of you like to say flip, the base. Now these 3 steps can be done in any order. Okay, but usually when I have a whole number raised to a fractional exponent, I always start in this order. I want to make my base as small as possible in case I have to apply a very big exponent to it, like 10 or 8 or 6. So I always take my root first. I always deal with my denominator first. So the first thing I'm going to do is take the cubed root of 8, and then I'm going to raise it to the negative 2 power. Okay, so I'm going to take care of the cubed root of 8, which is 2, and now I have 2 to the negative 2. Now some of you are okay to just finish this off from here, but again, if we go through these steps, we are now going to square the 2. Once we square the 2, we get 4. And remember, negative 2 is negative 1 times 2. So we've already applied the 2 to the base of 2, and we've gotten 2 squared, which is 4. And now we apply the negative 1. So that's our last step. And that just says invert, change the position of 4 over 1 to 1 over 4. Another word for that is the reciprocal. Okay, so that's our final answer, 1/4. Now, in the past, I've noticed sort of a big sort of misconception or error that student makes is that they remember something about that negative exponent dealing with flipping or inverting or finding the reciprocal of the base. And the mistake students make is that instead they flip the exponent. Okay, these 2 problems can't possibly be the same. You have 2 entirely different exponents. Sometimes I even keep the negative with it, even after they do it. But the point here is you never change the value of your exponent when you're doing exponent, when you're simplifying exponent problems. So this is a big misconception. Okay? So for those of you who like to see where these things come from, these properties, I wanted to show you why it doesn't matter which of these 3 steps you do at any one point. Because you can write negative 2/3, the fraction negative 2/3 like this, negative 1 times 2 times 1/3. You could write it as, now if we follow these 3 steps, we're doing the cubed root first, the squaring second, and then we're inverting the base. So this is the order we did, we evaluated 8 to the negative 2/3 with. So what other order could we have here? We've had negative 1's been the first one, 1/3's been the first factor. We could also square it, then cubed root it, and then invert it. We could square it, invert it, and then take the cubed root. Whoops, doesn't matter. So let's take a look at, let's see, we've done this one already. This is done right here. Let's do this one. Let's suppose we square it first. Let's try this one. So 8 raised to the negative 2/3 power. If we follow this rule, it's the same as 8 squared times negative 1/3. We're going to do this part first, and here's the exponent left. So if I square 8, I get 64. And now I want to apply the cubed root of 64 and then flip it. That's 4 to the negative 1, which is 1/4. So you see, it doesn't matter which order you do it in. Sometimes it's just a little easier, as I mentioned earlier, to take the root of your base first before the number gets too big. The only final thing I want to say is if you start when would I use something like this order, -1, 1/3, and then square it? I would use this order if I started with something like this. When my base starts off as a fraction, it's often easier to make it into a whole number by inverting it first, or as you would say, flipping it. So in this case, I would apply the -1 first, and then raise it to the 2/3 power, because -1 times 2/3 is -2/3. So I'm going to flip it, and I get 8/1, which is 8, and now 8 to the 2/3 is the cubed root of 8 squared, which is 2 squared, which is 4. So notice this problem here, 1/8 to the -2/3 and 8 to the -2/3, our answers are reciprocals of each other. Because notice our bases started out being reciprocals of each other. Okay, so that might have been a little more than you wanted to see, but I just wanted you to see that you could do this in any order and why the reason is that you could do that. And basically it's because you're taking this fraction and you're rewriting it as 3 factors. And since multiplication can be written in any order, how you take this apart and simplify it can be done in any order. Okay. Now see, we're moving on to another part of our prerequisite chapter that has to do with factoring. And when you see factor as your sort of order or your instructions, you have to recognize that now factor is being used as a verb. So you got to perform some kind of action. Whereas up here, when I wrote -1 times 2 times 1/3, these were called factors, and these are nouns because they're things. So your job here is to take this, you're going to take this subtraction problem that you have right here, and you're going to change it into an equivalent multiplication problem. So you're taking it and you're rewriting it as 2, 3, whatever the situation is, number of factors. So the first form of factoring that every student forgets about, and I used to make jokes saying, I think this should be for all algebra students, a little tattoo that they put on their hand, GCF, for finding the greatest common factor. This will often be your first step to help you factor any type of problem. So in this case, when I look at 5x cubed minus 4x squared, 4x, I notice that both 5 and x are common to each one of the terms that I see here. I see a 5 there, and I see a 5 and 45. Because 45 is 9 times 5, and each one of these terms have an x in it. So my first form of factoring is to pull out the 5x and say, what do I multiply 5x by to get 5x cubed? And my answer would be x squared. And then what do I multiply 45x by to get 9? Excuse me, 45, and I would say 9. Okay, so sometimes that's all you have to do and you're done. But you have to check to see if each factor is prime. So you take a look at 5 and you say, yep, 5 is prime. And you take a look at x, and x is prime. You can't factor that anymore. But this is a special situation that we can factor. This is not prime. So we can do one more step here in our factoring. And that step is how to factor x squared minus 9. This is called the difference between two perfect squares, or just between perfect squares, because x squared is a perfect square and 9 is a perfect square. So to factor x squared minus 9, these are the kind you like to see. The factors almost look the same. What do you square to get x squared? X. And that's in the first spot in the parentheses. What do you square to get 9? A 3. But notice you have 0x in the middle. You have no middle term. So if we put x squared plus 0x minus 9, it would be the same thing as this. In other words, if I wrote this, that's exactly the same as x squared minus 9, because this is just 0. So in order for your middle term and outer term to cancel here, or for you to get 0x in the middle, you'd have to add opposites. So you're going to put a plus here and a subtraction there. And now this is completely factored into prime factors. Every single one of these factors is prime. So this is completely factored. The only mistake students tend to make at this point is sometimes they'll get 5x times the quantity x squared minus 9, and then they go off on the side and they'll factor x squared minus 9 like this, and then they circle this as their answer, forgetting that the 5x is a part of it. Remember, whenever you factor an addition or subtraction problem, in the end, you should be able to multiply it back and come back to exactly the problem you started with. So that's always a little check you can do for yourself. Okay, now D is an addition problem. It's the addition of two fractions. In this case, they're called algebraic fractions or rational expressions. Those are all big terms for you to learn. But nothing changes. And the idea of what has to be true when we add or subtract anything in mathematics is that they have to be like. And in our preview exercises, we talked about like radicals, we talked about like terms. So in this case, we have two terms, and they're not the same because one of them has x plus 2 in the denominator, and one of them has x minus 1. So the first thing I always do is I put parentheses around my denominator, and that just helps me just see it. In this particular case, each one of these denominators say two totally different things. They cannot be factored. So in this case, each denominator is prime. So one little trick you could do for yourself is you could imagine, if you imagine that x equals 7 in this case, then what would we have? We'd have 3 times 7 on the top and 7 plus 2 on the bottom. And in the next case, you'd have x over 7 over 7 minus 2. So this would be the same as 21 over 9 minus 7 minus 2. The minus sign kind of got stuck in there with, let me make this a little clearer. Got stuck in there with the, I moved the whole thing away. Oh, it's a plus anyway, so I have to start this all over. 7 minus 2, there we go, plus 7/5. So if we were asked to add these two fractions, notice 5 is prime, and even though 9 isn't prime, it's made up of 3 times 3. So they don't share any common factors at all. So to find the multiple of these two denominators, you simply multiply the 9 times 5 together to get 45. So your job would be now to take 21 over 9 and make it equivalent, an equivalent fraction to some number over 45. Well, as you can see, the factor that's missing here in order to convert this is the other denominator, 5. So you have to multiply top and bottom by 5, which is really multiplying that 21/9 by 1. So you get 105 over 45. So this becomes 105 over 45. Plus, so now our job is to change 7/5 to an equivalent fraction that has 9 times 5 on the bottom. And you say, okay, here's my new equivalent fraction. What does my new fraction have in the denominator? 9 times 5. So what factor am I missing? I'm missing a 9. So I have to multiply the top by 9 and the bottom by 9, the numerator and denominator, which means I'm really just multiplying this by the number 1, which keeps everything the same. So now I have 63 over 45. So this now becomes 105 plus 63 all over that common denominator, which is 861 all over 45. So the job that I would have left here is to see if I could reduce this at all. So I know that 9 divides 45, and I know 5 divides 45. And since 9 divides 45, 3 is going to divide it. So now I have to say, can this number in the numerator be divided by either 3, 9, or 5 in order to reduce it? And I say, well, there's no way 168 can be divided by 5 because it doesn't end in 5 or 0. So then I say, well, how about 3? Well, a little trick you could do is if you add these digits together, 1 plus 6 is 7, plus 8 is 15. And since 15 can be divided by 3, guess what? This number can be divided by 3. So if I divide 168 by 3, I get 56. And if I divide 45 by 3, I get 15. So now I'm down to 3 times 5 are the only factors of 15. And since neither 3 or 5 divide 56, I'm done. That's reduced. So all I wanted you to see is that the process that you go through with arithmetic is exactly the same that you go through in algebra. So let's start the algebra problem. Okay, the first thing you do here is you take a look at each one of your denominators. And since each one of them is already prime and cannot be factored, you just simply multiply them together to get your lowest common denominator, or your multiple here, your lowest common multiple. And since you're putting it in the denominator, some people call it the lowest common denominator. So your job is to take 3x over x plus 2 and make it into an equivalent fraction. So what I'm going to do is I'm going to take this second denominator here and I'm going to make it blue, and I'm going to make my first denominator red. I like to work with colors a lot. I think it helps people to see what's going on. So I want to take this fraction and turn it into an equivalent fraction that has x plus 2 in the denominator, x minus 2, x plus 2, it doesn't matter which order we write it. And you compare the two denominators and you say, oh, this denominator has the red factor, same as this denominator, but what's it missing? It's missing the blue factor, x minus 2. So I have a right to multiply any fraction by any form of 1 that I want. So I'm going to multiply it by x minus 2 over x minus 2. So now my top becomes 3x times x minus 2 over x minus 2 times x plus 2. So at this point, remember, you've just done all of this work to change it to this new equivalent fraction. So don't start reducing this fraction by canceling out these common factors and dividing, which means you're dividing this by 1. Just leave it like this. So I often tell students to rewrite these things and just do this in the bottom, LCD, because that temptation to reduce before you even get a chance to add them often happens. So this becomes 3x times x minus 2 over the common denominator. Okay, so we've got one more fraction to add, one more fraction to make into an equivalent fraction. So let's take a look at what that is. This fraction has x minus 2 in the denominator, and I want to now make it an equivalent fraction that has x minus 2 as well as the red factor x plus 2. So when I compare these two fractions, I see my denominator is missing the factor x plus 2. So if I multiply the denominator by x plus 2, keeping everything equal, I have to multiply the top by x plus 2. So you can see if I essentially have multiplied this by the number 1. So this is x times x plus 2. So now here I have x times x plus 2 over that common denominator. So we're almost done. Now we get to add these. So you put one big long fraction bar like that. You put the LCD right there. Again, this LCD doesn't come into play until the very end when you see if you can reduce. At this point, you just want to simplify everything in your numerator. So our numerator is 3x times x minus 2 plus x times x plus 2. So let's see what this becomes. Make a little room here for us. This becomes one big long fraction bar, 3x squared minus 6x when I use my distributive property here, x squared plus 2x plus x squared plus 2x, all over my LCD. Again, I just keep it generic LCD. Now I can combine these two like terms, 3x squared and 1x squared gives me 4x squared, negative 6x plus 2x gives me minus 4x. Now I'll put in the actual values in my denominator. So let's see, what do we have here? Well, I could pull a 4x out of the top because I want to see if I can factor this at all. So I have 4x times x minus 4 over x plus 2 times x minus 2. And as you can see here, there are no common factors in the top and bottom. You don't see a 4 anywhere down here. You don't see a single factor of x. You don't see a factor of x minus 4. So this is considered completely factored and simplified. So that's it for the demo. You have lots of problems to work out that is similar to the different sections in the chapter P, the prerequisite chapter. Please let me know if you have any questions.